We have seen the notion of approximation, and we have given a proof of the main approximation theorem using the alter-measure. Now we give an alternative proof of the same theorem using the pi lambda theorem. It's a completely different proof, and it is a very interesting one. Remember again, what is the theorem? We have a probability space. We have an algebra of events on this probability space. All events in the algebra are in the sigma algebra of the probability space. And the theorem says for every event B in the sigma algebra generated by this given algebra of events, and for every epsilon positive, there exists an event A, and this algebra A, calligraphic A, that approximates very well B in the sense that the probability of the symmetric difference is less than epsilon. And we now show a proof of this approximation theorem using the pi lambda theorem. So the proof follows the same pattern as every proof that uses the pi lambda theorem. We have seen one already in a previous video lecture. That is, we define a class of set, which is the class of sets that satisfy the properties that we want, and in the end we show that this class is in fact big. It is the entire class of sets for which we claim this property to hold. And to start this, in the argument we always look for a class that is contained in D and that has the structure of being a pi system. And then we finally use the pi lambda theorem to conclude that D is large, so large that it contains the sigma algebra generated by it. And this is the second ingredient indeed. We take a class that usually when we're going to use pi lambda theorem, we take a class A that is contained in D, which is a pi system. And in this case, we're going to take A, the class, as the algebra itself. A is certainly a pi system because every algebra is a pi system. And why is A contained in D? Well, D is the family of sets in the bigger sigma algebra of our probability space or finite measure space. This family of events or sets that can be approximated by a set in A. Well, of course, if B is already in A to start with, then it can be approximated by an event in the algebra. That's for sure. We can take this the element in the algebra to be the same, B. So here we have the symmetric difference of B and B. This is the empty set. The measure of the empty set is 0. So this is trivially satisfied. So now we will prove that D, this class, is a lambda system. If we can prove that, then we get from the pi lambda theorem that D contains not only A, but contains also the sigma algebra generated by A. That is the content of the pi lambda theorem, and this will conclude the proof of our approximation theorem of today's lecture. And why so? The theorem is stating exactly that every set B in the sigma algebra generated by A satisfy this property. And this is exactly the property that defines our class D. So this concludes the proof of the theorem. We now just need to justify that D is indeed a lambda system. Now first, omega is in D. And why is that? Because we can take omega and omega here, and this is 0. 0 is less than epsilon, and this omega is our omega, and this omega is in the algebra A. Now, if B is a set in D, and we want to look at B complement, well, we know there exists some A in the algebra, such that the measure of A symmetric difference with B is less than epsilon. Well, we can also take a complement. A complement is also in the algebra because algebras are closed under complements, and this we can take with B complement. and this will also be less than epsilon. And why is it so? Well, because the symmetric difference between two sets is the same as the symmetric difference between the complement of those sets. So this checks the second property for being a lambda system. Now for the third property, we take a disjoint sequence of sets in this class D, and we have to show that their union is in D. Well, let B denote the union of these sets. Now, because we are working with a finite measure, we know that the sum of the measure of all these sets Bn will be equal to the measure of B, because they are disjoint, and mu is a sigma additive measure, and this is finite. Since this is finite, we know the tail of this series has to be small. So we can take k such that the sum of the terms after the kth term of this series, it gets small, less than epsilon over 2. Well, what is epsilon? It has not been quantified yet. Well, we should have introduced at this point, let epsilon be any positive number. Now to each of these Bn's, we can define An such that the measure of the symmetric difference between An and Bn is less than epsilon times 2 to the minus n. Let's put over 2 here to be sure. So we can make, what am I doing here? For each of these B's, which we assume are in this class, and this is the class of events that can be approximated arbitrarily well by sets in the algebra. And now I'm using, for the first time, the property that these sets actually are in this class by taking an element An in the algebra that approximates these Bn very well. And to conclude, we can take A to be the union of the finite union where n ranges from 1 to k of these An's. Since this is a finite union and these sets A, they are in the algebra A, then this finite union will also be in A, and now we just have to estimate what will be the measure. In order to conclude the proof, we just need to estimate what is the measure of the symmetric difference between A and B. And here, using the last property that we stated for the symmetric difference, which is this property here, that when we are comparing unions, we can group terms, we can make a correspondence between terms of these unions and compute the symmetric difference of each of them alone and take the union. And now coming back here, what is A? Well, we defined A as being the union of A1, A2, A3 up to AK, and we can after that add the empty set just to be complete. And what is B? B is the union, the infinite union of all the Bn's. We can just make them match, make them correspond one by one, and bound this from above by first the measure of the symmetric difference between A1 and B1, and keep going until AK and BK, and to complete, put here the empty set and then the remaining terms in this sequence BK. This will be less than epsilon over 4, then epsilon over 8, epsilon over 16, and so on until here, plus now the last term, which is just this union here, we can bound the union from above by the sum of all the measures. So this is less than epsilon over 2. So all these together are less than epsilon, which is what we had to prove. So we just provided an alternative proof of the approximation theorem using the pi lambda theorem.